Okay, so again, opening to page 70 in the packet, our quick look at the calendar shows us that this is the very last class of new material before our first test. So today we finish up with applications of systems of linear equations. So we'll do some more word problems today, just like last time. Then our very next class is our review day for the first test. But notice that our next class is not this coming Monday because it's Columbus Day. There are no day classes this coming Monday. So our very next class is Wednesday. That'll be our review day in preparation for our first test, which is a week from today, Friday next week. All right? And in terms of what's on the tests, well, it's everything. Classes 1 through 17, which means the test is more comprehensive than the quests have been. So how do you best prepare for the test? Well, you go over all your old homework, you go over the first 2 quests that we've had, and if you go to the packet, we're going to start on page 70, but I'm just going to skip to page 72 for just a moment, and you'll find practice problems for our first test. And I'll highlight again that if you go to YouTube and you know what you're looking for, you can find videos of me going through each of these problems. All right? So if you are able to spend some time over this holiday weekend, it's not too early to start studying for this test. The test is a week from today. It will be here before you know it. See if you can get a bunch of these done even before our review day coming up on Wednesday. Any questions on the schedule? Okay, then let's go back to page 70, and we'll start with our summary up here at the top. Can we go with Megan? Can you read the daily summary? Thank you. Dan, number 1. Okay, so the idea is we've got these standard concentrations of antifreeze. There's a 20% and there's a 25%. That just means that one of them has a little bit more of the chemical, which is called glycol, and a little bit less of the water. But we want to mix them in such a way that we get, we have a 20 and a 35. Those are the standards. And we want to mix them to try to make something that has a different concentration, a 25%. And this same type of scenario helps nurses and doctors figure out how to give the right amount of drug to a patient, right? You can't just say, well, go grab a bottle of 8% of this drug because that bottle might not exist. Maybe you have a 10% bottle and a 5% bottle, and you need to mix them in such a way that you get an 8% bottle, all right? So let's give this a shot. Part A says define your variables. So again, to figure out what the variables should be, where do we go in the problem? It's the very last part, which is the question. It says how much of each bottle should be in the mixture. So I'm going to call it, what am I going to call it? Low and high, I guess. So I'll let L equal the amount of 20% antifreeze. And we're always going to be careful when we define our variables to include units. What are the units for amount of antifreeze? The percent is, yeah, it's quarts. We're measuring the volume here in quarts. Okay, so you've got a bunch of this 20% antifreeze. It just means that 20% of that stuff is this chemical called glycol, and the other 80% is water. And then we'll do the same thing. I'll say H is the amount of the 35% antifreeze, also in quarts. Okay, so we're going to put some stuff into our table. Let me just make mention of something that has to do with the question one of you asked last class, is do I have to use the table to solve these problems? And the answer is no. I'm not going to say on the test, you must fill in this table. I'm not going to say anything about the tables on the test. In fact, the tables won't even appear on the test. Some people think that it helps them to organize all the information in a table, but if you're one of those lucky folks who can just write equations based on the information in the problem, that's fine. One thing I am going to insist on is that you define your variables clearly like we've been doing, and that you use algebra to solve the problems. Even if you can just kind of come to the answer by a little bit of trial and error, a little bit of intuition, it's an algebra class, and I'm going to expect you to do algebra on the test, right? So I don't need you to use the table, but you got to get to a place where you have equations, and then you got to solve them using algebra. Okay, let's start filling in. The percent glycol is the easiest part. In the 20% mixture, it is 20% glycol, but I'm not going to put 20 here. What am I putting? 0.2. I'll put 0.20. You don't need the 0, but just highlighting that we changed the 20% to a decimal. And then in the 35% solution, 0.35. Okay, and oftentimes this box has a line through it, but not here. We need to put a number in that box. This is supposed to be the final mixture. What's the goal concentration? Is 25%. So that right there is where we put the 0.25. Okay, let's move on to the first column, the amount of antifreeze in quarts. These are our variables. L was the amount of the 20% solution in quarts. So exactly L is what we put there. And then the amount of antifreeze of the 35% solution is what we called H. Yeah, and then the final mixture, again, is going to be a number. We find it in the problem. It's a total of 12 quarts that we're interested in. Yeah, that's exactly right, Jasper. Let's see if we can get to a place where Jasper is. I'm going to start in the bottom row. What I'm interested in here is the amount of glycol in quarts, the amount of glycol in quarts. Now remember, you imagine a bottle of antifreeze. Typically it's blue. Part of that antifreeze is this chemical called glycol, and the rest of it is just plain water, okay? So suppose that we look in the bottom row. We know we want 12 quarts altogether, 12 quarts in the bottle, some of which is the chemical, the rest of which is water. What we're saying here is that out of that 12 quarts, exactly 25% of it is the chemical, all right? 25% of this 12-quart bottle is the chemical, and the other 75% is water. If I want to know the amount of glycol, the amount of chemical, what do I do with the 12 and the 25%? We multiply them, right? How much glycol is in this 12-quart bottle? It's 25% of 12, which is just 3. Jasper? No, if you prefer the fraction 1/4, then you can totally use a fourth instead of the 0.25. I'm going to write something that is kind of redundant, but just highlighting that 3, it's not a percentage, it's an amount. It's the number of quarts of glycol that are in that 12-quart jar, okay? All right. And then if the basic idea here is that we multiply these numbers and put it over here, then it seems to be reasonable that we'll do the same thing in the first 2 rows. So Jasper, what did you say before about this first one? 120L. Do we buy it? All we're doing is multiplying the percentage by the number of quarts of antifreeze to tease out how much of that antifreeze is actually the chemical glycol. And then in the next one, 0.35H. Okay, so we've got our table completely filled in. Now it's time to write equations if we can. First equation comes from the green, that first column. What equation pops out from that first column? It's L plus H equals 12. See it? Our other equation comes from the last column in black. What equation do we get from there? 120L plus 0.35H equals 3. It's the amount of glycol from the first thing plus the amount of glycol from the second thing had better give us exactly the 3 quarts that we needed at the end. So those are our 2 equations. Again, in terms of the demo, I don't want to spend our time right now solving those 2 equations. I'm not saying it's easy, but it's something we've seen before. I just wanted to talk about the setup here. in the demo part. So if I've done things right, then you can check later and get these answers, 8 quarts of the first and 4 quarts of the second. But it turns out I don't always do things right. And so if you feel like going back and checking, Sam had mentioned that on this problem from last class on page 65, that Sam actually tried plugging in the 1.4 pounds of the one candy and the 3.6 pounds of the other, and they didn't satisfy our second equation. And he's absolutely right. I made a mistake when I typed this up. This one should have been 1.6, and this one should have been 3.4. So thank you, Sam. So if you went ahead and solved those, or you want to solve them later for practice, go ahead and fix my answer key because I made a mistake. What's that? Yeah, good. Okay, so one more problem in the demo, and it's down here, number 2. Let's go to Ashlyn for 2. Okay, so our basic equation is that the distance is equal to rate times time. This is something that we know to be true even if we don't have it memorized. But if you go 60 miles per hour for 3 hours, how far have you driven? 180 miles, right? That's something that you would naturally do. You naturally took the rate and multiplied it by the time to figure out the distance. Yeah, that's an equation we all believe. Okay, let's try number 3. We'll go to Nick. Okay, so we've got this airplane, and the airplane normally, if there's no wind at all, can travel a certain speed. And in this trip to Saratoga, this plane was going with the wind, and it took only 3 hours. But then when the plane turned around and made the return trip, it took longer because the plane was working against the wind. So our job is to figure out, well, what's the speed of the plane if there's no wind, and what's the speed of the wind? Now, of course, this is a simplification because the wind speed changes, and it depends on what altitude you're at, and depends on when you make the trip. But anyway, this is an intro into a kind of distance, rate, and time problem. So the first step, again, is to define variables. And to define those variables, we look at the actual last part of the problem. It says find the speed of the wind and separately the speed of the plane in still air. So I'll go ahead and let W be the speed of the wind. And again, we're going to put units. What are some good units for the speed of the wind? Miles per hour. And then I'll let P be the speed of the plane in still air in miles per hour. Okay, so let's start filling in the table. I'm going to go to this time column first. The first row is the trip to Saratoga, which is with the wind. How long did this trip take with the wind? It was 3 hours. And the bottom row is against the wind. How long was that? 5 hours. Took a lot longer because the wind was working against us instead of with us. Let's jump to the last column. Distance between Saratoga and wherever we start this trip. How long was it? 450 miles. How about the distance of the return trip? It's the same thing. It's also 450, but we need to make sure we use that 450 twice. Okay, and I'm going to put something in the very top row with our labels in it. I've got rate and time and distance, and we know that if we multiply rate and time, we get distance. So I'm just going to put this times here and it equals here. It's the same basic formula for every table we've seen. Even with the problems changing dramatically, it was the same basic idea, is if we set it up right, we're multiplying the first two columns to get the last column. It was true with the candy. It was true with the interest, where we invested some money. It was true up above with the antifreeze, and it's true here with this plane distance problem. Okay, so here's the tricky part. I want to know what the trip to Saratoga, I want to know what our speed was. Now, I don't have it as a number. I've got to include the variable W or the variable P, or maybe both of them. I'm just going to put a real quickie example over here. Suppose that I say that the speed of the plane by itself normally is 120 miles per hour, just making something up. I don't even know if a plane would stay up in the air going that slow, but we'll just make it up. And suppose that the wind speed is 10 miles per hour. If the plane is working with the wind, if they're both going the same direction, how fast is that plane really traveling? 130, right? We just have to add those two things when they're working together. When the plane is going against the wind, how fast is the plane going to go? 110 by subtracting those numbers. Yes? Okay, so all we have to do is put it here in terms of letters. So what do we do when the plane and wind are going the same direction? What do we do with our variables? Is we add them. P plus W. 120 plus 10. When they're working against each other, what do we do with those variables? Is we subtract them. Okay, there's two possible things here. I'm going to write them both, but only one of them is okay. If you put the wrong one, you're going to get into a whole lot of trouble algebraically. Yeah, the wind isn't flying, it's the plane. So the bigger number, hopefully, is the plane's speed, right? So which one is the right order? It's P minus W. But I'm just pointing out, you got to pause right there. And make sure you put them in the right order. Because if you put W plus P, that's fine. In the top row, it's fine. But W minus P in the bottom row, it's not okay. So writing our two equations is pretty straightforward. Rate times time is distance. P plus W, notice we got to put parentheses in here, times 3 is equal to 450. And then in the second row, multiplying the first two columns, P minus W times 5 is also 450. Questions on getting the two equations? Okay, again, I don't want us to spend time right now solving, but if you solve later, you can check your work or the answers. Turns out to be 120. Oh, did I make up that 120? Oh, I did. There you go. 120 happened to be the right number. And the speed of the wind was 30, right? But you can check that later. Okay. So moving on to the next page, there's good news. Here's the good news. The good news is the activity is your homework. So you can spend the next, how long do we have? 53 minutes doing your homework, perhaps finishing your homework, and maybe even starting those practice problems for the sample test. What I'd like to do, though, I think it worked well last time, was have each group start at a different place and then put the solutions up so that everybody has the solutions to every problem. We're going to go the other direction today, so everybody pay attention while I point to the tables to tell you where to start. You guys are number 1, you're number 2, you guys are 3, back there is 4, you're going to start with number 5. Okay, raise a flag if I can help.